guys, my name is Nako Nakatsuka. I'm a fourth year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. So to tie together a lot of things that we've talked about up until now, I wanted to talk about the two ways to approach reaction mechanisms. So the first is the direct computation, and this involves solving the differential equation and varying the values for K, or the rate constant, to get agreement with the experiment. The second way to approach this is to identify the rate determining step. Remember, this is the slow step that determines the rate. And in this case, we use the rate law of this rate limiting step as the overall rate, and we compare that model with the experiment. But within this second way to approach mechanisms, there's two different ways in which we can do this. A is called steady state. And what steady state means is that the concentration of intermediates in the rate limiting step is constant. So the intermediate in the mechanism, the concentration is going to remain constant over time. And so this indicates a steady state reaction. On the other hand, we also have pre-equilibrium. And as this term states, this is the reaction before the rate limiting step is at an equilibrium. And so you use its equilibrium constant K. And so now, since we haven't really talked about the pre-equilibrium approach, I'll show you guys a couple of examples of that. And so let's do an example where 2NO plus oxygen goes to 2NO2. So step one of the mechanism is a fast biomolecular dimerization. And so that's the combination, so that's why it's bi, because you have two molecules of NO dimerizing to form N2O2. And so the rate for this step would be written as K1 NO to the power of 2, because you have two of each. And then step two is a slow bimolecular reaction, where the oxygen molecule collides with a dimer. And so for here we have an oxygen colliding with this dimer that we formed to make NO2 plus NO2. And the rate for this reaction is K2 N2O2 O2 because of the two reactants. And so since I said that this was the slow step and this was the fast step, we know that this is going to be the rate determining step, right? And so if the early step is fast and the later step is slow, then there's a bottleneck, and a buildup of an intermediate results in the first step being approximately at equilibrium. And so from here, we can write it as the equilibrium constant. And remember, I talked about the difference between the equilibrium constant and the rate constant, right? Big K and little k. And so we can write the equilibrium constant as N2O2, which is the products, over NO squared. And remember that the concentration of N2O2 is going to equal this, if I rearrange the equation, right? And so step two, which is the slow step, determines the rate of formation of NO2. So this is the step that actually is going to determine the rate. And so for this part, for step two, let's write it out in terms of the rates. So we have 1/2 dNO2 over dt equals K2 N2O2 O2. So we can rearrange this by moving this 2 to the other side and doing the concentration of NO2 over dt equals 2 K2 N2O2 and O2. So from here, what we can do is we can actually substitute in some values. So remember that N2O2 is written as the equilibrium constant and NO squared, right? So since this equals this, I can actually take this part and substitute it in for the N2O2. And what do I get when I do that? I get 2K2 big K NO squared O2. And so this can be rewritten as 2K1 K2 over K1 reverse, because remember when I talked about the equilibrium constant, it can be written as the forward reaction over the backward reaction, right? And the backward reaction is indicated by the prime here. And NO squared O2. And as you can see, all of these rate constants are just constant values, so you can actually just group them together and call it K. And so the ultimate rate law that we end up with is K NO squared O2, where K equals this whole value. And this rate law that we determined right here actually corresponds to the experimental rate law. And so the value that we got from doing these two separate calculations gave us the actual rate law. And so the pre-equilibrium approach is simpler than the steady state approach, but it is less flexible. And if done correctly, the steady state and pre-equilibrium approaches give the same result. But as you can see in this case, knowing which step was fast, knowing which step was slow, we could write out one equation in terms of the equilibrium constant, the other in terms of its rates, and combine them together to figure out what the experiment rate law will most likely be.